Hello and welcome guys. In today's video we are gonna do the Hahn Banach theorem for complex norm spaces, and this is definitely one of the top 10 mind-boggling proofs in functional analysis. We are gonna use a combination of concepts from complex analysis, from functional analysis. It's gonna be a really nice, good ride. So let's look at the statement of the theorem first and then devise a strategy to deal with all the abstractions. So let X be a complex norm space. Let X be a complex norm space and X naught be a proper subspace of X, and F naught belongs to X naught star, which is to say that X naught star is the dual space of X naught and F naught is an element of that dual space. Now we are saying that there exists a F belonging to X star such that F restricted to X naught is equals to F naught and the norms are equal. So if you have seen in the theorem before us, it's the exact same statement, the only difference being that here X was a real norm space and X is a complex norm space in this case. Now what do I mean by a real norm space and a complex norm space? The only difference between a real and a complex space is that the scalars in the complex norm space are complex. So when I define the rules of my vector space, I always had this idea of scalar addition, of vector addition and scalar multiplication. So I had something like, okay, if I have v1 and v2 as elements belonging to my vector space V, then v1 plus v2 also belongs to V. Also alpha times v belongs to V for every value of V belonging to capital V. So this was my notion when I defined the vector space or rules of vector addition and scalar multiplication. So the difference is when I'm talking about a complex norm space, these alphas, these scalars are complex numbers. Complex numbers. So that's what a complex norm space is. And now let us look at the strategy of the proof, because since it's a huge proof, it involves big number of concepts, so we would look at how we're gonna go with proving the theorem. So in the previous video we proved the Hahn Banach theorem for real norm spaces. So what was given in the previous proof? We had inputs in terms of my space capital X, a subspace capital X naught, and a functional defined on it, which I denote by F naught tilde. So this is what's given to me, that F naught tilde is a functional from X naught to capital R, or should I say the space of real numbers, and F naught is real, F naught tilde is bounded, and it's linear. Now the theorem says that there exists F tilde from X to real numbers. See, here it was from X naught and here's from X to real numbers, such that F tilde is real, F tilde is linear, F tilde is bounded, and F tilde is equals to F naught tilde on X naught. So that's the same thing as writing this thing. The same thing is written here, but in a more relaxed way, in a more informal way, and the norms are equivalent. So F tilde norm is equals to norm of F naught tilde. So this was my Hahn Banach for real norm spaces. We did it in the previous video. Now what I have in this video is Hahn Banach for complex norm spaces. So the settings remain the same. The setting is again same, that there is a space capital X, a complex norm space, and X naught is a proper subspace of S. F naught is a functional defined from X to complex numbers, and F naught is complex linear, it is bounded. And now what the theorem says is that there exists a F from X to the set of complex numbers such that this f is complex linear, it is bounded, and that f is equals to f naught on x naught, the same thing being written here in a more informal way, and that the norms are equivalent. So that is what we need to do. That's the case scenario. Now, the way in which we do these kind of proofs is that, so if you look at this diagram, I know this, okay, I know this as the truth, and using this, I want to prove this. Okay, so this is the knowledge that I already have, and using this knowledge, I want to prove this theorem, the Hahn Banach for complex norm spaces. So we'd like to derive B from A, of course. So that is to show that A implies B. And how? So if you want to apply A, you somehow have to go to a real setting and somehow have to find a real linear bounded functional f naught. And how would we do it? We construct it somehow. So let's take a deep breath and go through the strategy, how we would proceed further with the proof. So the first thing we do is that we apply A to a suitable functional f naught tilde. So if I have this setting, now I have to find a functional f naught tilde so that I can apply A to it. So now that I have given an overview of what we are looking at, what we want, now I would look at a further strategy or an algorithmic way to deal with our abstractions now. So what I have is, in my setting for Hahn Banach for complex vector spaces, x0 and x are complex vector spaces. So they are real vector spaces also. Why is it so? So we have studied in high school that every complex number, and we have studied in high school that every real number is also a complex number. But here I am saying that if x and x0 are complex vector spaces, then they are also real vector spaces. Why? The reason is, by complex vector space, I mean that the scalars that I can multiply are complex. And by real vector spaces, I mean that the scalars are real. So now if I have a complex vector space, then if I just multiply by the real numbers, it can also be seen as a real vector space. So whatever theorems that apply for real vector spaces also apply for complex vector spaces, because complex vector spaces are real vector spaces. Now what are these scalars? If you remember, by the laws of vector addition and scalar multiplication, I always had that alpha times x is also belongs to x for every value of x belonging to x. Now this alpha in the case of complex vector space is complex, and in the case of real vector space is real. So that is what I mean when I say that all complex vector spaces are real vector spaces. So now if we go back to what we wanted to do initially, we had x, x0 and f0, and we wanted to find an f such that these two conditions are satisfied. So I will use this machinery or this algorithm here to further break down my analysis. So what I do next is I say that since x and x0 are complex vector spaces, they are real vector spaces, and for real vector spaces I had the Hahn Banach theorem for real vector spaces. So what I can do is, if I have this formulation and I want to use this machinery, so the way I would progress is I would define an f0 tilde to be the real part of f0. So this functional is from x0 to the complex number, and every complex number, so every complex number here can be divided like this. So every complex number roughly looks like this. So what I say is, whatever value this functional f0 gives me, I separate it into two parts. I define f0 tilde to be the real part of f0, this f0, for the case of complex norm space. And I say that whatever value I get, I take the real part of it and I define it to be f0 tilde. But now, if I have a real value as my codomain, I can use the Hahn Banach theorem for real norm spaces, because that's exactly what it said. It said that if you go up and look at the formulation, Hahn Banach for real norm spaces told me that if I had x, x0 and f0 tilde. Now remember, the trick here is so subtle, we did not change x and x0 because these are real norm spaces. Now, although in the formulation, in this case, they are complex norm spaces, but again, all that I mean by complex norm spaces and real norm spaces is, in this setting, I can only multiply by real scalars, and here I can multiply with complex numbers. So what I did was, I divided this, so whatever output it gave me, so f0 tilde gave me an output, say a plus iota b, and I took the real part of it. And once I have the real part of this, I would get a real number out of this. And if I get a real number of this, I can use this machinery. If you see, I can use this formulation here to extend it to find an f tilde. So you see, I can find a f tilde as a result of extension, because I have proved the Hahn Banach theorem for real norm spaces before. So once I did this trick, what do I need to do? I said that, okay, a gives me the extension of f0 tilde to f tilde, which goes from all of x to my r, such that f tilde is equals to f0 tilde on x0, and f tilde is real linear with the norms being equal. This I already know from Hahn Banach for real norm spaces. Now, if you look at this diagram that I drew before, you can see that, okay, this is the exact strategy that I am following. I had A, B, C, and I want to prove using A, B, C sum D. So what I already know is that alpha, beta, and gamma gives me delta. This theorem I know. So what I did was I converted this case into this case, and I got delta as a result. So similarly, in our case, this A and B, say, are complex vector spaces, so they are real vector spaces. The formulation of C, which was a complex linear, I took the real part of it, and therefore I got gamma, as in our case. And as a result of this gamma, I got delta, which is in our case is f tilde. You see? Now, what needs to be done next is, again, this f tilde needs to be converted into my setting for complex norm spaces. And how to do that? Let's check it now. So I have f tilde, which goes from x to r. It's a real linear. But I want to convert it to a f, which goes from x to c. It's complex linear. What do I mean by complex linear? Is that I can multiply with complex scalars. Okay, so f is from x to c, complex linear, such that f equals to f0 on x0, and the norms are equal. Now what to do, how to do this conversion back to my complex setting? Now, I define my f of x, the f of x which I wanted in the first place. See, this f I wanted in the first place. This was my setting. I had this input x, x0, and f0, and I wanted an f. Now what I say is that let me define this f in this way. Let me define f in this way and check if it works. Meaning that if I give you a formula, all you need to do is to check whether these two conditions hold. And if we can do that, then tada, we have our answer. Now, so far so good. Now the time has come to check the details. So till now we have devised a strategy, what would we be doing, and now we have to do it in real time. So I start with taking this norm of f naught to be equal to 1. So what was this f naught? It was in the complex setting. And remember, I would often be using this trick that I take norm of my operator to be 1. The only reason I do it is that it gives mathematical sophistication to my proofs. If I have norm of f naught to be equals to 1, I can cancel it every time. But if you don't like norm of f naught to be equals to 1, you can choose your own value of norm of f naught, but then the proof becomes very complicated and things become a bit difficult to handle. And I can always use this argument. I can always take my norm of f naught to be equal to 1 or norm of any operator to be equal to 1 because of the scaling argument. So now 3 steps are there. So first thing is that this f naught tilde, which I defined to be the real part of f naught, so the norm of f naught tilde x has to be less than norm of f naught x, of course, because real part of any complex number is less than the complex number itself. And now this is less than equals to norm of f naught times norm of x, and since norm of f naught is equals to 1, as you can see here, I can say that so norm of f naught tilde x has to be less than norm of f naught x because the real part of any complex number is less than the complex number itself, which has to be less than the norm of x because norm of f naught is equals to 1, and hence norm of f naught tilde has to be less than or equal to 1. Now I saw in the case before that I extended f naught tilde to f tilde, and since the norm of f naught tilde has to be less than or equal to 1, therefore the norm of f tilde is also less than or equal to 1. And now I need to check this condition. If you remember, I had to check this condition that it's complex linear with f is equals to f naught on x naught and that the norms are equivalent. So in order to check these 3 conditions, that it's complex linear with this and this, I would first check this condition. Now how would I check it? Let's see. So I have that for f of x is equals to f naught x for every value of x belonging to x naught. So I know that my f naught is complex linear, so I can multiply this iota inside. That's the condition for complex linear. If it's complex linear, you can multiply complex linear inside. Okay, and now I know that the real part of iota times f naught x, if I just do the real part on both the sides, it's just that. Just put the real part on both the sides. Now I know from complex analysis, or even if you don't know complex analysis, you can check for yourself very easily that the real part of iota times any complex number is equal to minus times of imaginary part of that complex number. You can check it for yourself. It's complex analysis 101, and that's why the real part of this is equals to the imaginary part of just this. So you would see that the real part of f naught x minus iota times the real part of f naught ix. Why am I doing this thing? Because I defined my f of x to be, f tilde x minus iota time f tilde ix, and for x belonging to x naught, this f tilde becomes f naught tilde. So I can say that f of x is equals to the real part of f naught x minus iota times the real part of f naught I of x. I did not do anything till now. I just substituted the definitions. I defined f of x to be f tilde x minus iota times of f tilde iota x. I defined it this way. And now for x belonging to x naught, I can write this definition. Okay. Now I know from this part that the real part of this quantity is nothing but minus times of imaginary part of this quantity, as from here you can see. So the transition from this to this requires this part. Now I know again that my f of x is equals to the real part of f naught x plus iota times imaginary part of f naught x, which is equals to f naught x. Now for every value of x belonging to x naught. So till now we have f is equals to f naught on x naught. Okay, I have one part. I had three different parts. I had to show that it's complex linear. I had to show that f is equals to f naught on x naught. And in the final setting, I had to show that the norms of f and f naught are equal. So now it's the time to check that f is complex linear. How would I check that? So f is obviously linear or real linear. What do I mean by complex linear again? What do I mean by complex linear is can multiply complex scalars inside the function. So I can take inside the function al. So just a quick reminder, complex linear means if I have iota times f of x, I can write it as f times iota x. Only if it's complex linear. If f is real linear, I cannot take this iota inside. So we know that f is obviously real linear because every complex vector space is a real vector space. Now I only need to check that f of alpha x is equals to alpha times f of x for every value of x belonging to capital X, where alpha is a complex number. Now how would I deal with it? I take my alpha, a complex number, to be alpha 1 plus iota times alpha 2, where alpha 1 and alpha 2 are real numbers. Now how would I write is f of alpha x, I again divide this f into f tilde into two separate parts by definition. See, this is what I had defined before. Okay, and now I substitute this alpha with alpha 1 plus iota times alpha 2. So that's this step. So this step is just substituting alpha is equals to alpha 1 plus iota times alpha 2. And now from this step to this step, I do not do anything. I just expand. Okay, I use the linearity argument. I just multiply my f tilde, I take it inside, I take the alpha ones out. Now one thing you would need to make sure in this setting is that I cannot take iota outside from f tilde because f tilde is a real linear, and in real linear I can never do things like taking the iota outside, because as soon as I take the iota outside, I assume that my f is complex linear, but that's what we want to prove. Okay, so remember, I cannot take iota outside in real linear, but no problem, I can always take the alpha outside. So now I take this alpha outside and I do the same computation here. I take alpha 1 outside and alpha 2 outside and write it as it is. So that's where, and now I take alpha common. So if I take alpha 1, alpha 2 to be the common argument. Now if I take alpha 1 and alpha 2 to be the common arguments, I get this form. But aha, this was exactly equals to f of x as per definition before. So I can, rather than writing this part, I can just write it as f of x, similarly here f of x. And now when I take f of x common, I'll just be left with, let me write down this step. I take f of x common and I'm just left with alpha 1 plus iota times alpha 2, which was nothing but alpha. So I have proved that f is complex linear. Now the only part that remains to be proven is that the norm are equivalent. So now we are at the last part of our proof. We have proved two things till now. We have proved that this f is complex linear and that f is equals to f naught on x naught, and the last thing that we need to prove is that the norms are equal. So let's check if f is bounded with norm of f is equals to 1. Now I know that the c is a complex number, and any complex number can be written in this form: mod of c e to the power I theta, where theta is the argument of c. So this is, again, you need to know at least this much, that any complex number can be written in this form. You'd find a million proofs on the internet how it can be written. It's 101, complex analysis 101. It's very simple. You'd find lots of resources on the internet to deal with this aspect. Now once you have this, I know that my f of x was a complex number. It gave me a complex number, and I can therefore write it as mod of f of x e to the power I theta, and theta is the argument of f of x. Now I have mod of f of x is equal to f of x e to the power minus I theta. I did nothing. I took e to the power I theta that side, and it became e to the power minus I theta. Now I know that this f is complex linear. So if something is complex linear, I can take this e to the power I theta inside of it. Complex linear. And now I know that mod f of x will give me a real number. There could not be any complex number in it. Okay, so mod of anything would give me a real number. So if that is equivalent to f e to the power minus I theta, then f e to the power minus I theta x is equal to the real part of it, because the modulus would never give a complex number. So if you have something like mod of f of x, so I can write it like, say, 3 plus 2 iota mod is equal to f of, say, x. Okay, suppose this. Now I can say that the modulus here is 9 plus 16 under root of 25, so I have it equals to 5. So this, if this is equal to a complex number, say this is a complex number, then f of x is nothing but the real part of f of x, because the quantity that I got from the left side of the equation was a real number. So I can write mod of f of x is equals to f of x e to the power minus I theta. I can take the e to the power minus I theta inside, and then since it is equivalent to mod, therefore I can write it as real part of f e to the power minus I theta x. And now I can put a mod on both the sides. So I know that my real part of f of y, okay, let me call this y. So if a real part of f of y is equals to f of y, and I put a modulus on both the sides, but this f tilde here, I know that this is less than equal to norm of y, because norm of f tilde was less than equal to 1, as I have shown before. And so this is true for y is equals to e to the power minus I theta x. So what I have done essentially is, let us look at this equation. Okay, so I have the real part of f of y to be this, and then if I see it in this way, so if I consider this as y, so real part f e to the minus I theta x has to be less than this y, which is exactly written here, and then I split it into two pieces, and the modulus of this is equals to 1. So the real part of f e to the power minus I theta x, modulus of the whole thing, is nothing but it's less than equal to norm of x, which implies that f of x is less than equal to mod of x, because I put that mod of f of x was equals to the real part of f e to the power minus I theta x. So from this argument I can say that mod of f of x is also less than equal to norm of x. But once I have this condition, I can conclude that norm of f has to be less than or equal to 1. And because f is an extension of f naught and norm of f naught was equal to 1, so norm of f also has to be equal to 1, and hence we proved the Hahn Banach theorem for complex norm spaces.